Hello everyone, I'm Rohit Kumar Singh, TA for this course Experimental Physics 2, and this is the 12th and last live session for this semester. So today I'm going to discuss some concepts of modern physics like photoelectric effect and atomic structure, and then solve some problems related to that. So let's start. So, first, I would like to discuss some. I'd like to remind you some of the concepts of photoelectric effect. So, do you all know what photoelectric effect is? I mean, you must have studied it earlier, right? Can anyone explain what photoelectric effect is? Which phenomena do we call photoelectric effect? So it's all in the name itself, photo and electric. Okay, so let me give you some insight. So, photoelectric effect is a phenomena in which when light is incident on a metal, electrons come out of the metal. Okay, so suppose you have a metal piece and it is bombarded by photons like this. So what will happen is that from inside the metal electrons will come out. Okay, and this phenomena is called photoelectric effect. Now this photoelectric effect is very important discovery because it is one of the discovery which leads to the particle nature of the light. And Einstein, Albert Einstein, you know him, he got a Nobel Prize for discovering it. Okay, so it's very important uh, in historic point of view. But to observe the photoelectric effect in our lab, uh, so can you guys hear me? Hello? Are you able to hear me fine? Fine, sir. Fine, sir. Okay, okay, thank you. Yeah. So, as I was saying, to observe this photoelectric phenomena in our lab, we can have a simple setup. So, what we can do is we can take a vacuum tube like this, okay, and place two. So place anode and cathode inside it, connected by wires like this. Okay, and some load can be applied here. You can connect an ammeter here to measure the current, and this will be the voltage applied. Okay, so this is the experimental setup which we can do, and then we can shine light on this anode. So this is the plus side anode and this is the negative side. Okay, and then we can shine light on this anode from above, and what will happen is that electrons will come out like this from this metal anode, right? And then these electrons will carry some kinetic energy, right? If when they are emitting outside, and they will start moving towards the cathode. But you see, electrons are negative charged, and this cathode is also negatively charged. So it should have a maximum kinetic energy uh, to reach here, unless if it has not a sufficient kinetic energy, it will not reach the cathode plate here, and you will not get a current. Okay, so now these electrons, the kinetic energy of these electrons can we can write a expression for that. So so the energy carried by photons, right? Which those which are striking the metal here. So the energy with which the photons strike the metal is h nu, right? And the energy carried by the electrons, so let's call it ke max. Okay, this is the maximum kinetic energy carried by the electrons. But it's not that all the energy that the photons give to the metal is converted into the kinetic energy of the electrons. Some energy will be required to just uh, so this the electrons are not freely moving inside the metal. So to break away from the metal, some energy is required, and that energy is called work function of the metal, and it's given by phi. Okay, so this is the equation of photoelectric effect, correct? But so you can see that some energy is getting lost in just uh, removing the electrons from the metal. Okay, just to take out the electron from the metal, and there is a threshold of frequency that is needed. So, and let's call it mu naught. So we can write phi as h mu naught. Okay, so if you shine a light with frequency mu naught on a metal, the electron will just come out of the metal with a zero kinetic energy. Okay, here K is Ke is 0. Okay, so we can write the above equation like this. And so the maximum kinetic energy that you can have in a photoelectron is just difference of these two energies. Okay, any doubt here, any question? Now this, yeah, please go ahead. Yeah, kinetic energy is half mv square. Yeah. So if you understood this concept, then any question on uh, photoelectric effect can be solved. Okay. So this experiment is very crucial. As I told you, it established the particle nature of light, uh, because the because if so there were some peculiarities to this photoelectric effect. For example, if you increase the intensity of light, okay, from classical some classical electromagnetic theory, you will believe that the number of electrons, the energy of electrons will increase. But that's not the case. Increasing the intensity does not increase the energy of the kinetic energy of the electrons. But what it increases is just the number of electrons. Okay. But when you increase the frequency of light, mu, then this kinetic energy of electrons increases. Okay. And below some threshold frequency mu naught, this phenomena stops. So these things suggest that these photons are not really behaving as a wave, right? It's behaving as a particle carrying energy h mu, which when struck on a metal, it delivers all its energy to an electron, okay, instantly, and then the electron comes out of the metal with kinetic energy K. Okay, so sorry. So, so this photoelectric effect establishes the particle nature of the light. Okay, you can read it in detail in many standard modern physics book. For now, we need only this much. Okay. Then I'll discuss some concept of atomic spectra. So, inside an atom, so inside an atom, we have many energy levels, right? And electrons and atoms also consist of electrons, and then electrons can jump from an excited state into ground into the ground state, or uh, below excited state, and emit photons, correct? uh, which we called atomic spectra. I mean, the spectra of those photons is called atomic spectra, right? So there is a very famous uh, so these things were established by Niels Bohr, and so let me let me write the energy with which the total energy of, so suppose, let's first take an hydrogen atom, okay? So this is a nucleus, okay, and you have one electron here. Now this electron can uh, so so first of all, the energy of this hydrogen atom is given like this: E square 8 pi epsilon naught r, okay, where r is the radius of the uh, orbit of the electron, okay. And this energy is negative, okay, because it reflects the fact that it is bound to the nucleus. And if you were to take this electron out of this atom, then you have to provide an energy equal to this positive energy, correct? So, and then what you can have is so you can shine a light of wavelength lambda, which is h by mv, correct? uh, Wait, so we cannot write it for wavelength. So you can shine a light E equal to h mu, which can be written as hc by lambda. And if this energy matches this energy, then the electron can be ionized, right? So it is same phenomena which we observe here in the case of photoelectric effect. Okay, and then uh, there are many levels, a level of energy for uh, any atom, okay, and this is called uh, so so basically there are many wavelengths in the spectrum of an element, and this is called a spectral series, okay. And the wavelength, so if an electron transition from an excited state to a different excited state, the wavelength of light that is emitted can be calculated by this formula. This is a very well known formula. So this is the wait, this is the final state and n square, and this is the initial state, where r is the Rydberg constant. Okay, and it's given as 1.097 into 10 to the power 7. Okay, and there are many series, a spectral series named as Lyman series, Balmer series, uh, P-Fund series. So let me discuss some of them. Okay, so in case of Lyman series, our Ni, so in each our final state can be, should be 1. Okay, that means first that means the ground state. Okay, and Ni can be 2, 3 up to infinity. So the Lyman series, for Lyman series, this formula becomes 1 by 1 square minus 1 by n square, where n is equal to 2, 3, 2. Similarly, for Balmer series, Nf is 2 and Ni can be 3, 4, 5, so on. Okay. So for this, the formula is lambda r 1 by 2 square minus 1 by n square, where n is 3, 4, 5. So these things also you must be knowing. Okay, so I think this is all we need. So and also some things uh, just to help us do the calculation. You know the value of Hc? So the value of Hc is roughly 1240 electron volt nanometer, correct? And it can also be written as 12400 sorry, yeah, this is the value. So this value help us in calculation, so just remember this. Okay, yeah, okay, so let's now go to our, so does anyone have any question till here?
Sir, what is the last expression? Is equal to 240 nanometers, sir?
Yeah, electron volt nanometer.
Electron volt.
Yeah.
Nanometers, sir. EV also.
Yeah, EV nanometer. So this HC has the unit electron volt nanometer. Okay. Okay. Anyone else? Any question? Okay. If not, let's go to our first problem. So yeah, and also, I mean, instead of nanometer, we can write it as 12, uh, one more zero, and then we can write it as EV angstrom, correct? So this can also come in handy. So yeah, we'll see. So let's look at our first problem. Can everyone see the problem, or should I make it bigger? So here the problem is the surface of a metal is illuminated with the light of 400 nanometer, and the kinetic energy of the ejected photoelectrons was found to be 1.10 electron volt. So the work function of the metal is, so it's a very straightforward problem. We have been given uh, frequency of the wavelength of the light which is falling on the metal, and kinetic energy of the photoelectrons is given, correct? And we are asked phi, the work function. Okay, so we have this formula that uh, the energy which of the light which is illuminated on the metal is equal to the kinetic energy plus phi, work function, correct? And you can write it as hc by lambda is equal to plus phi. So work function is minus kinetic energy. Now here you see, for hc we can write 1240 electron volt nanometer, and lambda is given 400 nanometer, right? And kinetic energy is given 1.10 electron volt. So here nanometer will cancel, and 1240 divided by 400 is just 3.1 electron volt minus 1.10 electron volt, and this will be just 2 electron volt, which is the answer. So here the answer doesn't matches to anyone, so D is the correct option. Okay, so yeah, I mean, remembering the hc value in this form is very easy while solving the problem. Fine. This was a very simple problem, very simple application of photoelectric effect. Any question here?
It seems that
Yeah. Is there?
unfortunately you could is by lambda, sir.
Yeah.
140 by 140 EV nanometer by 400. The surface of the metal illuminated by light 4 nanometer. This is voltage in lambda.
Yeah, so Lambda I have divided here, no? 400 nanometer. I couldn't understand your question. Can you please say it again?
Each every problem, suppose in the coming examination that is the same crops, same model, same problem, compulsory use this formula set 140 EV by 400.
Yeah, yeah, you can. Yeah, you can use this. Yeah,
Okay, sir, thank you, sir.
yeah. Okay. So then let's move to our second problem. Okay. Here the question is, when monochromatic light of wavelength lambda is incident on a metallic surface, the stopping potential for photoelectric current is 3V0. Okay. When the same surface is illuminated with light of 2 lambda, the stopping potential is V0. Okay. The threshold wavelength for this surface when photoelectric effect takes place is. So it is asking us the threshold wavelength. Now, as I told you when I was discussing photoelectric effect, so the electron which comes out of the metal has to reach the cathode here, okay, and it will depend whether the kinetic it has enough kinetic energy to reach the cathode here, because electrons are negatively charged and this cathode is also negatively charged, so there will be a repulsion, right? And since we are applying a voltage here, uh, voltage here, so we can change the voltage, and at certain potential V naught, the electron will not reach here. Electron will not have sufficient kinetic energy to reach here. Okay. So let's uh, call that wavelength lambda naught our threshold wavelength. Okay. And so first, for the wavelength lambda, we can write the photoelectric equation, which is it's C by lambda is equal to, so as I told you, the work function is given by h mu naught, which is hc by lambda naught with the threshold wavelength. So work function plus, so the kinetic energy here, uh, so since the stopping potential is 3V naught, that means is it is matching with the kinetic energy, maximum kinetic energy of the photoelectrons, correct? So Ke max will be 3V naught in case of lambda, and then V naught in sorry 3, because kinetic energy has uh, unit electron volt, so we have to multiply E into it. Okay. So 3 EV naught for the lambda and EV naught for the 2 lambda case. Okay. So kinetic energy we can write as 3 ev naught. Do you understand why I am writing kinetic energy as 3 ev naught?
Understood, sir.
Yeah, because
V is equal to kinetic force.
yeah. So, and for the 2 lambda, we can write the same equation as hc by lambda naught plus, here we have the kinetic energy as ev naught. Okay. So, we have two equations. What we can do is we can multiply this by 3 and then subtract from above equation. So then what we'll get is, so 3 hc by 2 lambda minus hc by lambda will give us hc by 2 lambda, correct? And this will cancel, sorry, not this will not cancel, this will cancel, and here we'll get 2 hc by lambda naught, and by solving this we will get 4 lambda is equal to lambda naught. So we have calculated the threshold wavelength, which is just 4 lambda. Okay. So at a wavelength 4 lambda, there won't be any photoelectrons coming outside the metal. Okay. So this simple experiment can be used to calculate the threshold wavelength for this metal surface. Okay. Any question here? So you have to understand, not just apply the formula, but really understand what's going on here. Okay, why I am taking kinetic energy max as 3 ev naught?
Sir, excuse sir.
Yeah.
Any direct formula is there, sir? Any direct formula?
Any
Any direct formula?
direct formula?
Okay.
No.
Some shortcut is any shortcut mode is there, sir? Never problem.
I mean this is the sort. I mean this is the most shortcut way you can have.
Okay.
I mean, so these two information.
Any relationship with their lambda and their step, no? Ratio and so on.
No, I mean there cannot be any shortcut way to calculate this threshold wavelength. So this information given in the problem, it is enough to calculate it this way. Okay, you just have to write two photoelectric equation, and from there you can calculate the threshold.
Okay, sir.
Correct? Because see, if you have just given one information here, then it won't be enough, because see, you have uh, you have two unknowns here, right? And you need at least two equation. So yeah. Okay, then let's move to the next problem. So here it is asking the ratio of minimum wavelengths of Lyman and Balmer series. Okay, so I just showed you the formula for wavelength for Lyman and Balmer series. So let me write it out once again. So for Lyman, what we have, so let it write as lambda f, Rydberg constant 1 by 1 square minus 1 by n square, right? Where n is 2, 3 and so on. And Balmer, we have the final state as n equal to 2. So 2 square minus 1 by n square, where n is 3, 4, so on. Okay, so now we need the minimum wavelength. So minimum wavelength means maximum energy, right? So for maximum energy, what should be the uh, initial state for both? Should it be the infinity or 2 or 3? What do you think? Anyone? For minimum wavelength, what should be the this n here? Can anyone answer? You should be able to answer. Hello, can you hear me?
Yes, sir. Sir, you asked this 104, sir.
What?
Answer is 104, sir.
No. I'm not asking the answer. I'm asking you what what will be the initial state to have the minimum wavelength? What will be the n here in the both cases?
In the first case, minimum energy, sir, n is equal to 2, sir. Bounce n is equal to 3.
Okay. So you are saying for this case, for Lyman also n equal to 2, for Balmer you should have n equal to 3.
Yes, sir.
Okay, anyone else? Does anyone agree with that? Is it correct? Everyone agree with that? So it's wrong, okay? For minimum wavelength, that is for maximum wavelength, both should be infinity. Okay? I mean it's visible from this formula here. So you need minimum wavelength. That means you need this quantity to be as less as possible. So whatever you subtracting from here should be 0, right? And to make it 0, you should have n equal to infinity. Otherwise, it won't go to 0, right? So it's the simple logic. So then we can calculate 1 by lambda L is equal to, it will just R because this one is 0, and 1 by lambda B is, so this is 0, so 1 by 2 R by 2 square, which is just 4. And when you'll take the ratio of lambda L to lambda B, it is just 1 by 4, correct? So I don't know how you knew the answer, but yeah, your logic was wrong. So okay, think about it. Anything you want to say?
Sir,
Yeah.
suppose in the same problem, the ratio of maximum evidence of alignment Balmer series means is asking minimum.
Oh yeah. So for maximum, this is correct. N equal to 2, n equal to 3. Okay. Yeah. As you go higher and higher, you need more energy. That is, for more energy, you have less wavelength. Correct? Because energy is inversely proportional to wavelength. Right? Yeah. Okay. Then let's go to the fourth problem. Okay. Here, A and B are two metals with threshold wavelengths 6200 angstrom and 4100 angstrom respectively. Two identical photons of energy 2.5 electron volt each are incident on them. Then photoelectrons are emitted by A alone, B alone, both A and B, or neither in A or B. Okay. So we have two metals with and whose threshold wavelength is given. Okay. And we are and the photons are incident on them carrying energy 2.5 electron volt. Okay, so then we have to find from which of the two metals the photoelectrons are emitted. So how to go about solving this? Anyone? Any idea? So first of all, let's calculate the work function. Okay, so you know that work function is h mu naught, right, or hc by lambda naught, and the lambda naught is the threshold wavelength which is given here. So let's calculate the work function for A first. So hc by lambda naught, hc is what, 1240 eV nanometer, but we have the lambda here in angstrom, so just add one more zero, then eV angstrom, and divided by 6200 angstrom. Okay, so this will be just 2 electron volt, correct? And similarly, work function for B is hc by lambda naught is equal to 12400 divided by 4100, which is 3 electron volts. Okay, now you have the work function for A and B. Now tell me from which the photoelectrons are emitted.
Ask B, sir.
Option B.
B.
Oh, you're saying only why B? You need 3 electron volt.
The energy greater than threshold is 3 electron volts.
Yeah, but you need less energy, right? What is work function? Work function is the minimum energy you need to get the electron out of the metal. But the minimum energy you have here, so the maximum energy you have here for photon is 2.5 electron volt. How can it overcome an threshold energy of 3 electron volt? You need at least 3 electron volt to get the electrons out of the metal B, right? So only A can emit the photoelectrons because it has work function less than 2.5 electron volt, correct? So option A alone is correct. Okay, anyone has any question here?
Sir, you are right. You are writing on the HC by lambda value. HC into C value. You again explain, sir. H into C comes at 12400 eV angstrom nanometer. Again, you write to the right, sir. On the
Oh, so you are saying how I am writing this value?
yes.
Okay. So
Something in the class constant last apply to understood.
yeah,
Again, the two it's C value again you write, sir.
yeah.
Again you have to clearly mention, sir. It's C value.
Okay. So you know the value of H. It is 6.67 into 10 to the power how much?
Minus 31, sir.
Minus 31 or and
31, sir.
okay, whatever. And C has is 3 into 10 to the power 8, correct? It's in meter per second and it's in joule per second. No, joule second or something, right? Wait, it is C by lambda. Joule
Second.
by second or joule second? Yeah. Okay. So to convert it, so first we have to convert the joule in electron volt, right? So 1 joule is equal to what? 1 point, yeah, minus 19 electron volt, correct? So this you have to multiply it into this to convert this into electron volt, and you can convert meter into nanometer or angstrom, correct? By multiplying it from by so 10 to the power 9 nanometer, right? So this way you will get that the formula comes as, I mean, this way you will get this value 12,400. Okay, you do this by hand, okay, by using a calculator. You will get the same value. Okay, this was your confusion, right? Okay, so then let's go to our next problem. So what is the ratio of minimum to maximum wavelength in the emission spectra of Palmer series? So again, we have this problem on emission spectra. So just uh, I mentioned, so for Balmer series we have this formula 2 square minus 1 by n square, n going from 3 4 to above. Okay, now for minimum, again tell me what will be the value of n. I just told. For minimum, n is equal to infinity, right? So then from here lambda, sorry, lambda minimum is just wait, 4 by r, correct? And then for lambda max, what will be the n? Yeah, 3 square. Okay, so then we can calculate lambda max as, so it will, if you calculate, it will be 36 by 5 r, correct? So then you can take the ratio of lambda mean to lambda max, which you will get as 5 by 9. Okay, so option A is correct. Okay, simple one. Any question here?
So coming to 30th examination, you are writing exams. That is same models are having same models.
Same
Type of problems are.
yeah, same. There will be same type of problems. Yeah. I mean, if you know the basic concepts, it will not be much difficult. Okay. Yeah. So let's go to the sixth problem. And here we have to find out the minimum energy required to take out only one electron from the ground state of lithium plus ion. Okay. So we have one electron on at a ground state. Okay, to take out means to ionize this. Take out, take out this electron. That means to ionize this electron, this atom completely. Correct. And how do we do that? So you know the energy. Uh, so for hydrogen atom, I've written the energy. For any atom, the energy of a state is given as this. Correct? Where Z is the atomic number and N is the state in which the electron is. Okay. So here, since the electron is in the ground state, N is equal to 1, and Z is the atomic number of lithium, which is 3, right? And to ionize this lithium ion, uh, so to ionize this lithium ion means what? Which which state we have to take the electron to? What should be the final state? Anyone? So we have to take the electron to infinity, right? Then we can say that it's ionized completely. So that means the energy of the final state is 0. So the total energy that we need here is just 13.6 into 3 square by 2 square. Sorry. One square. If you calculate it, it will be 122.4 electron volt. And but this negative sign is as I told you, this reflect that the electron is bound to the nucleus. So the energy that you need to give is positive 122.4. I mean, it's just the convention, but in answer you should I mean, you can get confused whether to write negative or positive. So if you are asked how much energy is required, then you must answer the positive one. Okay, this negative is the energy of the system. Okay, and this negative sign shows that it is a bonded system. Okay. Yeah. Okay, next problem. So three beams, one of red light, one of violet light, another of blue light of the same intensity are incident on a metal surface to emit photoelectrons. Okay, which emit electrons of greatest kinetic energy. No, this is just a qualitative question. There is no calculation needed here. Can can all of you answer this one? Please answer this one by one. Let's see who is correct. So first I'll call Derangula. So Satnarayan, wait, I'll ask you. So Derangula, can you answer this question? Which option is correct? If you cannot speak, you can write in the chat. Hello? Derangula? Violet. Okay. Uh, then Harsh. So one vote has gone to Violet. Harsh, can you answer it? It doesn't matter if it's right or wrong. Harsh, can you hear me?
Maybe answer the red light, sir, red light.
You're answering red light.
Yes, sir.
Okay, one vote to red light. Anyone else? Kavita? Sahida? What do you think? Which is the correct answer? Hello? Okay, Sahida is answering Violet. Okay, one more vote to Violet. Kavita, Harsh, are you guys answering or still thinking? Okay, so the correct answer is Violet. Okay. Now the reason for this is, so as I told you, there is a metal surface. Okay, light is incident on it, and so suppose the intensity. So what is the measure of intensity? So intensity means number of photons. Okay, number of photons in the beam. So if the number of photons in the beam is more, the intensity of light is more. Okay, but the kinetic energy of the electrons which are emitted from the metal surface does not depend on the number of photons. It depends on what? It depends on the frequency of the light, right? So you see from the equation of photoelectric effect, it is h mu minus h mu naught, which is the threshold frequency. So it doesn't depend anywhere on the number of photons, the kinetic energy. It only depends on the frequency of the light mu, right? And out of blue, violet, and red light, you know that the violet light has the highest frequency, Vibgyor, right? Uh, so this way the frequency decreases, correct? Violet has the highest frequency. So that's why the violet will emit the electrons of greatest kinetic energy, because it will deliver more energy inside the metal, and so the electrons will have more energy when they will come out of the metal, correct? Intensity has nothing to do with the kinetic energy of electrons. So this is one of the most peculiar thing about photoelectric effect. No matter how much intensity you provide, if your frequency uh, of the photons does not exceed the this work function, no photoelectrons will be observed. Okay, no matter how intense your beam is, you need more frequency, not intensity. Just remember this. Okay. Okay, Satnarayan.
Okay, sir. Clear understand.
Okay. Okay, then eighth problem. If the intensity of incident radiation in a photocell is increased, how does the stopping potential vary? Again, a question that I need you to answer. Again, we are increasing the intensity of the incident light. So, how does the stopping potential vary? What is the stopping potential? Uh, so the stopping potential is determined by the kinetic energy of the photoelectron, right? Kinetic energy max. If it matches the stopping potential V naught, uh, we can stop the photoelectrons from reaching the cathode, correct? So the kinetic energy, so the stopping potential is given by this formula, as I mentioned before. V naught is stopping potential. Now answer: if the intensity is increased, does the stopping potential vary? Will the stopping potential vary? We'll have to vary the stopping potential or not? Again, can you guys answer one by one? Option A, B, C, D. Does it increases, remain the same? Yeah, Satnarayan.
Ask me, sir, increases.
Increases. Okay, one vote to increases. Anyone else? Shahida, Dirangula, Harsh, Kavita. Anyone? Again remember, the intensity is changed. Okay, we are just varying the intensity. Okay, one more vote to increases. Anyone else? Shahida, what do you think? Others also not responding. Harsh, Kavita, think about it. Shahida, you not answer? Okay, so, okay, think about it. So again, you guys are wrong. I just told you, see, this kinetic energy, it depends on the frequency, right? And this stopping potential depends on the kinetic energy of the photoelectrons. And kinetic energy depends on the frequency of the light, not on the intensity of light. So, even if you change the intensity of the light, no matter how intense your beam is, you does not have to vary your stopping potential to stop the photoelectrons from reaching the cathode. So it should remain the same. Okay?
Sir,
Yeah, okay, I'll explain. So this is your beam that is incident on the metal plate, okay? And here you have applied some potential V, okay? And electrons are coming out here going towards the cathode. Now these electrons will are carrying the kinetic energy. This kinetic energy depends on what? Frequency of this beam, right? Not on the intensity of the beam. Correct? And the potential that you are applying here to stop this electron from reaching the cathode, it should match the kinetic energy of the electrons coming. Correct? Then only you can stop it from reaching here. And since this stopping potential depends on the kinetic energy, and kinetic energy in turns depend on only the frequency of the light, so changing the intensity will not change the kinetic energy and hence will not change the stopping potential. Okay? Yeah. So basically changing the intensity in photoelectric effect does not causes anything. It causes one thing only. You will have more photoelectrons, more and more photoelectrons, but with the same kinetic energy. Okay? The kinetic energy won't increase. Just the number of the photoelectrons will increase. So yeah, these are the strange things about photoelectric effect. So you should remember this. There will be questions like this in the exam. Okay, so yeah, think about this a little bit more. Now let's go to our ninth problem. If the frequency of the incident radiation is equal to the threshold frequency, what will be the value of the stopping potential? Okay, so what is given here is, so you have frequency of the incident radiations mu is equal to the threshold frequency, that is the minimum frequency needed to uh, take out the electron from the metal. Okay, then what will be the value of stopping potential? Okay, so what do you think? What will be the answer? We don't need to solve this problem also. So what will happen when the frequency of the incident radiation is just equal to the threshold frequency? So you have the formula, right? Kinetic energy max is h mu minus mu naught. If mu and mu naught are equal, then kinetic energy max is 0, right? And since the kinetic energy is 0, you don't need any potential to stop the electrons because they are already stopped. Kinetic energy is 0, right? So the stopping potential will also be 0. Understood? You need a stopping potential to stop the photoelectrons from reaching the cathode, like I told you here. You applied this stopping potential to stop this electron from reaching here, but they are already stopped here. Kinetic energy is 0 here. Okay, so you don't need any stopping potential. You need 0 stopping potential. Is it fine?
Yes, sir. Fine, sir.
Yeah.
But here music will not do. Again, kinetic energy means so potential is equal to 0 also.
Yeah.
0, sir.
Yeah.
Okay, sir.
Okay. So, okay, then 10th problem. The maximum kinetic energy of a photoelectron volt is 1 electron volt. Photoelectron is 1 electron volt. What is the stopping potential? Okay. So, again, we have the formula. Ke max is equal to h mu minus work function, correct? And also Ke max is equal to EV naught, where V naught is the stopping potential. Correct? So this is given 1 electron volt Ke max, and this is EV naught. So we can so that means V is just 1 volt, right? The stopping potential. It's a simple problem. Right? You don't need this equation here. I just wrote it. Uh, Let me erase it. Okay, this was the simplest problem. Let me go to the last problem. Now this problem is a little bit involved. So let's read it first. Given that the longest wavelength in emission spectra of Lyman series is 1000 angstrom, then the highest frequency emitted in the emission spectra of Balmer series is. Okay, so how do you approach this problem? Anyone, any idea?
So using formulas, the same formulas, 1 by lambda L equals to R into 1 by M1 square minus 1 by M2 square.
Yeah, okay, so for Lyman we have, yeah, this formula 1 by 1 square minus 1 by n square. Okay, now this lambda given is the longest wavelength. So when do you have longest wavelength? When n is equal to what? To have longest wavelength, n is equal to what? Think about it. I told this before. We need lambda max. Lambda max is given. So for this, what should be the n? Is it infinity? Infinity? No, wrong. For the minimum wavelength, infinity is correct. For longest wavelength, maximum wavelength, n is equal to 2, right? Yeah. Thank you, Devangala. So, lambda max is given 1000 angstrom or 1 square minus 1 by 2 square. Yes, Satyanarayan, you want to say anything?
No, sir, no problem.
Okay. Okay. So that is 1 by 1000 is equal to 3R by 4, right? then okay, so from here you can calculate the value of R, which is uh, 4 by 3000, correct? Rydberg constant for now. Now you the question asks the highest frequency emitted in the case of Balmer series. So highest frequency means what? Lowest wavelength, right? Because frequency is inversely proportional to wavelength. And for lambda mean, what should be the n here? So it is 2 square in the case of Balmer series. So what will be the n here? Again, for minimum, infinity or 3? Infinity. Here infinity. For the case of minimum, it should be infinity. Again, Shahida, you are wrong. You are just giving opposite answers. So you have to think about it, okay? So minimum, for minimum, lambda minimum, uh, I mean, you have to think it like this way, okay? So this negative sign is there. So what will you have? So for 1 by lambda minimum means it is a maximum quantity, right? So this whatever you are subtracting should be 0, and to make it 0, this 1 by infinity should be there. Okay, so then you can calculate uh, minimum lambda, which is equal to just 4 by r. Okay, and we lambda minimum is equal to, so we can put in place of r this one. So 4 into 3000, so it is just 3000. But what we need here is the frequency. So how to change from frequency lambda to frequency? So mu, this will be max, right? C by lambda mean, correct? This is the formula, right? Frequency is equal to C by wavelength, correct? So let me calculate it here. C is what? 3 into 10 to the power 8 divided by, what is the lambda mean? 3000. Right? And this is in this 3000 is in what, angstrom, right? So we have to multiply it by 10 to the power minus 10, and when you calculate it, so 3 will cancel with 3, 8 zeros are here, and this 10 will go here, 18, and this 3 will cancel, so we'll have 10 to the power 15 hertz. This is the correct answer. Okay. So did you understand this problem? So first what we did is, so here the longest wavelength for Lyman series was given. So we use this formula for Lyman series and we calculated, we put lambda max, and for maximum we know that uh, the this initial state should be 2, right? So we put 2 here and we calculate the expression for R. Okay, and then the question was asking the highest frequency emitted in Balmer spectra. So for highest frequency we need minimum wavelength. So we use minimum wavelength formula for Balmer series, and for minimum wavelength we know that the initial state should be infinity. Okay, so we put infinity here and we got the expression for minimum wavelength, and then using this C by lambda formula we calculated the maximum frequency, highest frequency. Correct? So think about this. And do you have any question here right now? Anyone?
No, sir.
Okay. Did you understand it? So yeah, I mean, it gets little bit confusing. So you have to really think about it. Okay, just don't remember the formula. Think about what is happening. Okay, then you will be able to solve the problems easily. Okay, so any other question, anything you want to ask? So today, this is the last time we'll meet for this semester. Okay, and if you want to ask anything, you can.
Thank you very much, sir. You are explaining very excellent manner, sir. Very grateful to you. Thank you, sir.
Yes, thank you. Thank you
Sir,
for attending.
I request you to,
Yeah,
sir,
yeah.
if possible,
Mm-hmm.
you give some important formulas, 5 minutes, sir. I'm very grateful to sir. Only formula, sir. You writing on the formula. You are writing on the formula, sir.
You
And
want?
the examination were very useful, sir. That's why I request you to some important formulas you can writing on the your writing here, sir.
So you want me to write some important formula for you?
Like something experimental physics around 20 formulas you follow.
Yeah. So
All the assignments also no problem, sir.
yeah. So see, whatever I have taught, I mean this 12 live session, I always what I do is start with writing some formulas, the important formulas that you need. Okay. So, and these slides are available on the NPTEL website. Okay.
Okay, sir.
So you can go on the NPTEL website, look at my slides, and you will get all the formulas that you need in the exam. In the first 2 slides, I always write the formulas. Okay.
Okay, sir.
So you will find all the relevant formulas that you need, and then I start solving the problem. So you can also look at the previous problems that I have solved. So you will find everything on the NPTEL website. My all slides are there. Okay. This one I'll also upload it by tomorrow. So you will also find this one. Okay. Yeah. Anything else? Anyone? Okay, if not, then I'll close the session today. And all the best for your exams and your future. Okay, thank you so much.
Thank you. Thank you.
Thank you.